Hey guys, this is a video tutorial about pressure in a liquid. So we're just going to cover the basics today about what factors do we think affect pressure in a liquid, and we're going to figure out what that is today. So I want to start with this tank of water here. Let's say it's just a regular old tank of water, and we poke 3 holes, 1, 2, 3, at various depths. What do you think is going to happen when we unplug these holes? Do you think the water will come out evenly, or do you think there will be more water coming out of certain holes? So think about that for a sec. And hopefully you said the bottom hole will actually experience the greatest amount of flow, and the top one will experience the least amount of flow. So this is actually what it would look like. And if you haven't tried this, I definitely recommend it so you can see it for yourself. But as you see here, the top has the least amount of flow, then the middle one, and then the bottom hole has the greatest amount of flow. So what this is suggesting is that perhaps the deeper we go, the more pressure there is. Whoops. And this makes sense, right? Because we know that when we go into a swimming pool and if we get to the deepest part of the deep end, sometimes we can get an earache, right? Because there's a lot of pressure. So this kind of confirms that the deeper we go, the more pressure there is in a liquid. So what else is involved? Well, let's take a look at a quick example, because that's the best way to kind of figure it out. So we have Andy and April here, and they are on a quest to find a new sea anemone to live in. So that's kind of not important, but what is important right now is how much pressure is each one experiencing. So let's just take a look at some numbers. What if I told you that April is 55 meters below the surface of the water, and Andy is 52 meters below the surface of the water, and April has a mass of 12 kilograms, and the area of contact between the water and her is 0.3 meters squared, whereas Andy has a mass of 18 kilograms and an area of contact of 0.37 meters squared. Which of all of this information do you think is most important? Does all of it matter? Do we want to use all of it? Well, we've already confirmed that depth matters. So when we question what determines the pressure in a liquid, we know that depth is really important, right? And it turns out that something else that's really important is the density of the fluid. So whether they're in salt water or fresh water, or whether in oil, or maybe even they're in honey or something really thick like that, that is going to change the pressure that they're experiencing. And just as a reminder, density is a measure of mass over volume. You probably remember that from a chemistry class. And I'm just going to tell you right off the bat that let's consider that this density of this salt water here is 1,035 kilograms per meters cubed. And the kilograms is the mass, which it's mass over volume, so it's over meters cubed. So far we know that depth is important, and then the density of the fluid also matters when it comes to pressure in a liquid. And there's one more thing that we can include in our calculation, because if you think about it, there is a bunch of air that is pushing down on top of the ocean, and that is actually impacting the pressure that they experience, because we don't feel it every day, but the air is actually pushing down on us. There's a weight of the air on us. And so that is also important in this calculation. So this will tell us like the absolute pressure that they're experiencing. So the pressure from above the fluid is also valuable. And like other areas of physics, there is definitely a mathematical expression that can help us to figure out how would we calculate this. How would we calculate April's pressure, and how would we calculate the pressure that Andy is experiencing? Well, the expression P2 equals P1 plus this crazy new symbol here called rho times gravity times height. So what are each of these? What do they mean? Well, let's take a look. So we have pressure 2, P2 is pressure at the depth that we're talking about. So For April, it would be whatever pressure she's experiencing at this depth of 55 meters. For Andy, it's the pressure that he's experiencing at his depth. So that is equal to P1, which is the pressure from above the fluid. Now, where would this be coming from? As I just said, it's coming from the air. So the air is actually pushing down on the ocean. And so we're going to have a number for that, and I'll give that to you in a second. Then we have density. So this crazy symbol rho is the symbol for density in physics, and we'll be using that both here and when we start buoyancy. And then we have gravity. Gravity, which we're very familiar with, is 9.8 or 10 meters per second squared. And then the H stands for height/depth, I like to say, and it's specifically the height between P1 and P2. So in this case, P1 is the pressure coming from above, so that would be here, and P2 is down here where April is for April's pressure, and so the height would be this 55 meters. For Andy, the pressure 1 is up here and the pressure 2 is here, so it's only 52 meters. So let's actually go ahead and calculate the pressure that both April is experiencing versus Andy. So we'll start with April, and we'll just go ahead and use this equation. So April's pressure at her depth, which would be P2, is equal to P1, and 1 is actually caused by the air, and it's called atmospheric pressure, or PATM. And there's a specific number that we're going to use for atmospheric pressure. It's specifically 101,325 pascals. So you can write that down and remember that number. And then we have plus rho, or density. And we said before the density of the salt water is 1,035 kilograms per meters cubed. So we'll go ahead and add that, times gravity, which we know is 10, times height. And for April, it's 55 meters because that's between P1, which is coming from the atmosphere, and P2, which is the pressure she's experiencing. So it's 55 meters there. So when we do our lovely algebra, and you want to make sure to multiply these first and then add your atmospheric pressure, we get a whopping 569,250 pascals. So it seems pretty straightforward, right? It'll take a little bit of time to get used to the formula and this crazy symbol here, but I want you to go ahead and try to solve for the pressure that Andy is experiencing using the same formula. So pause the video and try Andy's pressure real quick. Ready, set, go. All right, let's check it out. Hopefully you got it correct. So Andy's pressure at Andy's depth. We're going to use the same exact formula, obviously, and the only thing that changes is actually the height, because it's the same air, same atmospheric pressure, the same density of water, because they're in the same water. Gravity doesn't change, and the only thing that changes is the height. So it's going to look exactly the same except for the 52, and you should have gotten 538,200 pascals. So if you did anything wrong, it might have been in the algebra, so check your work, and hopefully you got it correct. Now I want you to notice something. You were given this information here, April's mass and her area, Andy's mass and his area. Did we use that? No, we didn't. We only used the values that were in this expression here. So when it comes to pressure in a liquid, we're only going to be dealing with these factors. So if you ever see a problem with extra information, don't feel like you have to use it if it's not necessary. So let's look at some takeaway points for so far. So we know that pressure in a liquid can be determined by the following expression. This beautiful thing right here. And there are a couple common values that I want you to write down and that we can use in the future. So you can assume that these values, unless stated otherwise, so in the two problems, I gave you the density of the salt water. Sorry, in the first problem, I gave you the density of the salt water. But just as a reminder, density of fresh water is 1,000 kilograms per meters cubed. And so we'll be using that pretty frequently. And then the standard air pressure, or atmospheric pressure, is 101,325 pascals. So you can go ahead and write that down as well as a number that you'll be using frequently. So let's do one more, and I want you to try it on your own. So we have Leslie here, and she's checking out two beautiful fish on her scuba diving adventure. Leslie has a mass of 50 kilograms and an area of 0.4 meters squared in contact with the water. The water has a density of 1,030 kilograms per meters cubed, and the atmospheric pressure is 101,325 pascals. Sorry, 101,325 pascals. If she's experiencing 190,000 pascals of pressure where she's at the depth that she's at, what depth is that? What depth would she have to go to experience this amount of pressure, this 190,000 pascals of pressure? So it's a slightly different approach to this problem, but we are still going to be using this expression for pressure. And so using your notes and filtering out which information in this description is important and what information is not important, I want you to go ahead and pause the video and try the problem. Ready, set, go. Okay, let's check it out. So we got P2 equals P1 plus density times gravity times height. So for P2, hopefully you realized that P2, as you remember, is the pressure at the depth. So the pressure that she's experiencing right now is 190,000. So I'll just go ahead and put this all out here. So 190,000 is the P2. P1 is atmospheric pressure. So it's the pressure above the fluid. In this case, it's caused by the air, which is the PATM. Plus density, which you were told was 1,030 kilograms per meters cubed. And we know gravity is 10. And then we're actually looking for height. So before we were looking for P2, but now we're looking for height. So the only thing mathematically that changes is that our algebra steps are going to be a little bit different. So let's just see how it plays out. You should have first subtracted the 101,325 PATM from both sides, because remember, algebraically, that's our next step. And then we can multiply these two together, and then once we do that, those cancel out, and we're left with the left side equals 10,300 times height. We divide, and we're left with the depth, or the height here between P1 and P2 is 8.6 meters. So that's how far Leslie is below the surface, because the surface is P1 and her depth is P2. The pressure there is P2. Hopefully you got that right. Great job if you did. If not, double check your algebra, and that's it. So thank you guys so much for watching, and make sure you write down any questions you have. You can ask me later.